Hello. This will be a demonstration of proposition 6 from book 4 of Euclid's Elements, which requires us to, in a given circle, inscribe a square. We've done all that we can do with triangles, and so now we're moving on to squares. We are given the circle A, B, C, D. So we have some circle, A, B, C, D. And given the circle, it is our task to inscribe a square in this circle, A, B, C, D. We begin by drawing a diameter of this circle, A, B, C, D, and we'll call this diameter A, E, C. So drawing a diameter is a combination of finding the center, which we do by 3, 1, and we'll call this center point E. We then join the straight line EA by postulate 1. And then we produce it to the other end of the circumference by postulate 2. Next, we draw the straight line BED perpendicular to AC at the point E. Like so. So these would all then be right angles because BD is perpendicular to AC, which is by proposition 111. What also follows is that this straight line, BED, is also a diameter of the circle. You can clearly see that. It's a straight line going through the center, so it's a diameter. Finally, we join the straight lines AB, BC, CD, and DA, like so. We do that all by postulate 1. Now, knowing that the straight line BD is a diameter of the circle, we can say by definition 115 that BE is equal to ED. And we know that the angles, all the angles at E are right angles, and so postulate 4, they're all equal. And so the angle AEB is equal to the angle AED. And we have this straight line, AE, which is common to both the triangles ABE and ADE. And so these two triangles, ABE and ADE, are equal in all respects by proposition 1, 4. These are two triangles which have two sides equal to two sides, and the angle contained by the equal sides equal as well. So these triangles are equal in all respects, namely that AB be equal to DA. Now we can prove in a similar manner that the triangle AED is equal in all respects to the triangle CED, which means that AD and CD are equal. And again, we can show that the triangle CED and BEC are equal in all respects, and so BC is equal to CD. And finally, that the triangles AEB and BEC are equal in all respects, and so AB is equal to BC. Which means that all four of these straight lines, AB, BC, CD, and DA, are equal to each other, all by combination 1, which means that the whole quadrilateral ABCD is equilateral. All of its side lengths are equal, and so it's equilateral. Next, the segment here, the segment of the circle, BAD, right here, it's cut off by a diameter. So by definition 118, this segment BAD is a semicircle, which means that using proposition 331, the angle in a semicircle is always a right angle. And so the angle BAD right here is a right angle. Now, again, we can prove in a similar manner by showing that all of the segments here, ADC, DCB, and CBA, all of these are semicircles, which means that by proposition 331, the angles in them are right angles, which means that the angle ADC, DCB, and CBA are all right angles, which means that the quadrilateral ABC, all of its interior angles are right angles. And we also had shown that the quadrilateral ABCD is equilateral, and so this quadrilateral ABCD is simultaneously equilateral and right angled, which satisfies the definition of a square given in definition 122, which means that the quadrilateral ABCD is a square, and that means that in our given circle ABCD, we have inscribed the square ABCD. Now this is what we set out to do, which means we're done with the proposition QEF. I have nothing to add to this proposition, so I'll simply end it here and move on to 4.7.